So here we go with problem number 3. All right, in problem 3, we're looking at how many joules of heat are required to raise the temperature of 30 grams of water by 50 degrees. So once again, you have a change in temperature. So you're going to use the change in temperature formula, which is Q equals mCp delta T. In this problem, we know the mass, 30 grams. We know the specific, we're not given the specific heat capacity in the problem. But at the top of the page, we're given the heat capacity for liquid water. It's 4.18 joules per gram degree C. And since it says we're dealing with water, that's the specific heat capacity that we will use. And then the last thing is delta T. It says we're raising the temperature by 50 degrees. So the problem becomes simply multiplying the three numbers together. So 30 times 4.18 times 50 equals 6,270. So that's our Q value for that problem. Next question says we're at 10 grams of water at its boiling point. So I'm going to draw a little graph sketch over here. This is that graph we've been talking about. And we know that at the boiling point, Q was equal to mass times heat of vaporization. That's a V. And down here, Q equals mass times heat of fusion. In between, anytime there's a temperature change, temperature's on the y-axis. Anytime there's a temperature change, you use Q equals mCp delta T. Well, here we're at the boiling point, so that means we're up at the top, right there. So we're going to use the formula Q equals mHV. The mass is 10 grams. The heat of vaporization is listed at the top of the page as 2,260, right there. So we're going to go ahead and use the 2,260. So 10 times 2,260 equals 22,600 joules. Grams have canceled. So 22,600 would be our final answer on that one. Okay, number 5, how much energy must be removed at 0 degrees. So you see in this one, we're at the melting point because 0 degrees is right here. So if I put temperatures on there, whoops. That would be 0. Up here would be 100. So we're at 0. So we're going to use a formula that we use when you're at the melting point, which is MHF. So Q equals MHF. The mass is 25 grams, and heat of fusion at the top of the page is listed as 334. So now I need to multiply those two numbers together. 25 times 334 is 8,350. Okay, for the last one, we're at steam again at 100 degrees, so we're up at the boiling point. So we're up here. We're going to use the mHV formula since we're at the boiling point. This time we know 565 joules. Joules measure Q, or Q is measured in joules, because that's the quantity of heat. So you'd have 565 joules. And then you would have the mass. You don't know the mass because you're looking for how many grams. The heat of vaporization is listed at the top of the page as 2,260 joules per gram. Notice that we do not use the 100. It's only there to tell us that we're at the boiling point. Now to solve for m, divide both sides by what? 2260. So 565 divided by 2260 looks like 0.25 grams. So m equals 0.25 grams. Not very much. Okay, down here I'm going to write down what the molecules are doing. If you're melting something, molecules have to start moving faster. As you're going from liquid to gas, molecules move faster. Condensing means going from gas back to liquid. So molecules move slower. Freezing means going from liquid to solid. So the molecules are going to slow down again. So the phase changes that release energy would be where the molecules slow down. So that would be these, where they're moving slower in both condensing and freezing. So those would be your two answers. Number 8, scandium has a specific heat capacity of 0.568 and iron's 0.449. Specific heat capacity is the amount of energy needed to raise the temperature of something. So it takes more energy to raise the temperature of scandium than iron. So which would get hot faster? Well, it would be the one that took less energy to make the temperature go up. The one that requires less energy to make the temperature go up. So that would be iron. So given the same amount of heat, the piece of iron will have a higher temperature because it doesn't take as much heat to make it get hot. If you had the other test, the answer was gold, because gold doesn't require as much heat to make the temperature rise. All right, for these last two questions, we're going to use this graph again, so I'm going to redraw temperature on the y-axis. Go up, over, up, over, up. Okay, if you're at this temperature right here is 0. So it's, I can redraw here. So this temperature here, 0. This temperature here, 100. So if you're starting at -10 in number 9, -10, you're going to be down below 0. So if you're somewhere in this area, if I can get my pen to work right. Probably is working right. Just not doing what I want it to do. So you're down somewhere below 0, down in there. Somewhere in there. And 110 is up here. Somewhere up in there. So you're going to have to go up, over, and up. So you're going to have 5 steps to make this calculation. So that answer was 5. Now the quantity of heat needed to go from 30 to 110 in number 10, you're going to need 30 somewhere in here. Somewhere in that area. So 30. And 110 somewhere up in here. So it looks like it's 1, 2, 3 steps. So anytime the temperature changes, you use Q equals M Cp delta T. During the boiling point, that's this top plateau, it's going to be Q equals M HV. And the final temperature change would be another temperature change equation, Q equals M Cp delta T. All right, so for the first one, the first area would be from 30 to 100, because you got to go from 30 up to the boiling point. So from 30 to 100. So the mass, same every time, is 100 grams. Specific heat capacity, 4.18. In order to keep from getting real jumbled up, I'm going to leave the units off. And the delta T is 70 degrees. All right, so you'd have 100 times 4.18 times 70. 29,260. So that's how much energy it takes. That'll be in joules. That's how much energy it takes to go from here to here. Now we got to cross the plateau. That's mass times heat of vaporization. So you got 100 grams, and I'm going to leave the units off again. So 2260 joules per gram. 2260 is the heat of vaporization that we used previously. So you're looking at 226000. All right, and then the last step, you've got 100. And now we're in the steam range. So you're going to use the 2.06 number that I gave you. And the delta T up here is from 100 here to 110. So that's only a 10-degree change. All right, so 100 times 2.06 times 10, get rid of that, is, I don't know, 100 times 2.06 times 10. So, of course, 206, so it's 2,060. It's 2,060. All right, so 2060 joules, and this was in joules. So now if I add those three numbers together, the 2,060 plus the 226,000 plus the 29,260, I get 257,320 joules. And that would be the total energy necessary to get up, over, and up. So up, over, up. 3 steps. Final answer, 257,320 joules. All right, I'll come back later and do 11 and 12.